Hello, class. So on this video, we'll continue on section 2.6. It's actually going to be the last video. And then we're going to move back to section 2.1. Right? We're finally going to go back to that section which we skipped. Now, before I start on this video, let me just remind you real quick what we did in the previous video. Right? Basically, what we did is I gave you an algorithm about or for solving a differential equation like this. So given that we know that this differential equation comes from an expression like this, right? A function of f of xy equal to a constant, such that when we take the derivative with respect to x on both sides, we get the original differential equation back. If we know that is true, I showed you the process of how to find such function. Right? So we basically use the fact that we know that this partial derivative is equal to this part of the differential equation. Right? So you integrate with respect to x, and then you get this form for your function. How do you solve for this part that we don't know, this h of y? Well, you use the other part. The fact that we know that the partial of this function with respect to y equals this part of the differential equation. So you take the derivative of this expression you found with respect to y. That way you can solve for h prime of y, which in turn says to solve for h of y. The other thing we mentioned is this distinction between an explicit solution of a differential equation and an implicit one. So an explicit solution of a differential equation is when you can solve for your function, your solution, right, your y, explicitly as a function of x, meaning that you can solve for y on one side of the equation by itself, everything involving the independent variable and constants is on the other side. When you can do that, that's called an explicit solution. If you can't do that, or you don't do that, so this was an example where I said, okay, any y that satisfies this expression is also a solution to the differential equation. So I'm not giving you what y is explicitly. I'm just telling you whatever y satisfies those are the solutions. So in such case, we're actually just writing it in the form f of xy equal to z. Again, whether it is because you can't solve for y or because you haven't. And if you leave your solution like that, just as some expression, f of xy equals a constant, such solution is called an implicit solution because we haven't solved for y explicitly as a function of the independent variable. And as I mentioned in the previous video, in this case, you can solve for y. It's a little bit of work because you have to remember how to do completing the square. But in most cases, it's not going to be the case that you can solve for y. And in fact, or it's going to be very hard. And in fact, in most cases, it's not going to be the case that there is a function such that when you take its derivative, you get the original differential equation. And that's important, right? Because what that means is, okay, if I don't know, if most of the time I can't find such a function f, then there's no point in going through all this work. So the next question is, when do I know that such a function f exists? So I can actually go through all this work and find it. And that's what the next theorem is. Okay. So in terms of the numbering, again, I mentioned that I messed up in the previous videos because I was doing the numberings based on lectures, but that worked last summer when it was face-to-face and I had more time. So I mentioned a couple of videos ago that I'm just going to redo the numbering every time I start a new section. So that's why there's going to be some scribbles. So I apologize about that. Okay. So theorem 1, an ODE of the form some expression involving x and y's plus some expression involving x and y's times y prime equal to 0. And that's exactly the form we have here. This would be our m. This would be our n. Such a differential equation is said to be exact, right, which I defined in previous videos, but I remind you again what it is, meaning that there exists a function of two variables such that the partial derivative of f with respect to x equals m, and the partial derivative of f with respect to y equals n. Right? That's when we say this differential equation is exact. And when does that happen? Well, it's a very simple test. Take the partial derivative of m with respect to y, and that should be equal to the partial derivative of n with respect to x. If that's the case, then you know that such a function f exists, and it's worthwhile, and we can actually go ahead in doing all this process that we did to find such a function, okay? And in fact, we can see, using this differential equation here, we can see that this isn't exact, right? We can now guarantee that it is the case because we look at what the differential equation is. Let me see if I wrote it right. 2x plus 3, 2y minus 2. 2x plus 3, 2y minus 2, dy dx equals 0. Let's see, or let's try to check whether this is exact. Okay, so we already know from the previous work that it is, because I already gave you the function and we found it, but let's check. So when you're trying to test this condition, whatever is multiplying your derivative, that's always your m, always. Everything that's left over is always your m. So let's check. Let's see what the partial derivative of m with respect to y is. Okay. Well, there's no y's in m, so for our purposes, everything is a constant, so this is 0. And now let's take the partial derivative of n with respect to x. Look at n, there are no variables x, so for our purposes, 2y minus 2 is a constant. So that is also equal to 0. Right? We get equality, meaning that this differential equation is exact, meaning that there is such a function, so we can actually go ahead and find it. Okay. So it's a very simple condition to check. Now, there are some continuity assumptions that you don't have to worry about. You learn about them in Calc 3. For our purposes, these continuity assumptions are always satisfied, so you don't have to worry about those. All you have to worry about is checking this condition. Okay? So let's do a quick example. Okay. So is the differential equation 2x plus y plus x plus 6y times dy dx equal to 0 exact? If so, find the general solution. Okay. So again, let's just check our conditions. As always, whatever is multiplying your derivative is your m. Everything left over is your m. So let's check. Partial m, partial x, partial y. What is that going to be equal to? Well, 2x goes to 0, and then y goes to 1. The derivative of that with respect to y is 1. So here we get 1. Now let's see partial n, partial x. X goes to 1. 6y is a constant for our purposes, so that goes to 0. So that's also equal to 1. So this differential equation is exact. Meaning that we can actually go ahead and go through all that work we did in the previous video to actually find the function f of xy. And again, how do we do that? Well, we use the assumption that, what does it mean for a differential equation to be exact? It means that m, which in this case is 2x plus y, is the partial derivative of our function, which we don't know what it is, we're trying to find with respect to x, and n, which in this case is x plus 6y, is the partial derivative of our function with respect to y. So we use those assumptions and basically follow the same process as before. Okay, so using the first assumption, we know that m, or in our case 2x plus y, is the partial derivative of our function with respect to x. So let's integrate 2x plus y with respect to x. So we get x squared plus xy. Why do we get xy? Well, remember that y is a constant, right? So the integral of a constant is just multiply that constant by the independent variable. So again, for our purposes, whether it's taking derivatives with respect to x, partial derivatives with respect to x, or integrals with respect to x, the other variable is always a constant. So this integral is equal to this plus, now not just the constant, but some expression involving y, the variable y, and constants. Why? Because again, when we take the partial derivative with respect to x, we know that any expression involving y's goes to 0. So we lose that information when we take the partial derivative with respect to x. So we want to make sure to include that information in our integral. So we know that our function has this form, x squared plus xy plus some expression involving y's and constants, which we don't know what it is. That's using this first assumption. Now let's use the other assumption. The fact that n equals the partial derivative of f with respect to y. Okay, so let's write that out. Partial derivative of f with respect to y, well, we know what f is. It's x squared plus xy plus h of y. Right, so the partial derivative of this with respect to y, this has to be equal to our n, right, by assumption, our x plus 6y. Okay, so let's go ahead and find what this partial derivative is with respect to y. So x squared is a constant for our purposes. That goes to 0. X times y, again, you're taking the derivative as you would with respect to y, treating x as a constant. Right? So this term, all you're left with is x plus the derivative, the partial derivative of hy with respect to y. Since there's no x's there, it's the same as saying the derivative with respect to y, the regular derivative. So this is h prime of y. And of course, by assumption, this has to be equal to x plus 6y. We can cancel the x's on both sides. Right? So h prime of y equals 6y. Integrate both sides with respect to y to find h. So this would be 3y squared plus a constant, right, of integration. Now that we found what h of y is, we can just go ahead and plug it in into our function. So what do we have? Well, we know that f of xy equals, so we have x squared plus xy plus h of y, which we found to be 3y squared. And like I mentioned, you don't have, you can just forget about the constant now, because when we set it equal to a constant, that already takes care of that. So you can just leave it like this. And again, this is not the solution. So if you were doing this in the homework, there's one more thing you would have to write. You would write something like this. Any y that satisfies, f of xy equals c, which in our case is x squared plus xy plus 3y squared equals c, is a solution to the differential equation. Another way you can write this is, or so let me just write it alternatively. Alternatively, x squared plus xy, oops, it looks like a y. So x squared plus xy plus 3y squared equals c is an implicit solution, or is the general implicit solution. So it's the general solution, just read it implicitly. And either way you write it is fine. Either write it as an implicit solution or state what happens, right? That any y that satisfies this expression is also a solution to the differential equation. And then that's basically it in this section. Right? It's basically, how do you determine when a differential equation is exact? Once you know it's exact, how do you find the implicit solution? Okay. So that's it for section 2.6. As I mentioned, in the next video, we're going to go back to section 2.1. The reason why is because, as you see here, this differential equation is not linear. Right? You can go ahead and check that it's not linear very easily. If, for example, look at whatever is in front of the derivative, in this case, this, and there are y's there. You know that that's bad. That means it's not linear. So basically, all of these methods that we've seen so far, which are basically a separation of variables and exact differential equations, all of those work for linear or nonlinear ODEs. Right? That's it. You don't necessarily need your differential equation to be linear. From now on, all of the methods that we're going to be looking at are going to be for linear differential equations. And that is why I skipped section 2.1 all the way till the end. So I can separate it into, okay, methods for nonlinear ODEs, and now methods for linear ODEs. There is one more method that I'm going to introduce of how to solve nonlinear ODEs, but that's going to be given in the homework, later, future homework. In terms of lectures, this is the last method we're going to see for nonlinear ODEs.